Well, welcome Nitin Chidambaram, sorry, from UNED. Welcome to Spain. Thank you for starting the seminar, the MaPhyAG seminar for this year. And thank you for talking about this Gaiotto State from topological recursion. So,
cool. Well, thanks a lot, Marina, for the invitation. I'm very happy to give a talk. And in fact, I was supposed to give this talk at some point last year, and then there was like the biggest storm and like floods in Madrid. So, but anyway, now I'm happy to finally be giving this talk. So basically, I'm going to talk about some work that I did. It's based on two papers, one with Gaiotto and Orantin, and Thomas Kreuzig, and the other one with Gaiotto and Orantin and Giacomo, which is more recent from last year. And it's about like Gaiotto vectors and their relation to topological recursion. So I'll try and give like a very sort of broad overview talk, so I won't get into too many details. Okay, so let me start by giving you some motivation for this. So basically, one of the kind of main objects that we're looking at is the so-called Nekrasov partition function. Okay, so I'll denote that by Z. This is a pretty well-studied object from gauge theory. I'll sort of, I mean, you don't need to know anything about really gauge theory. I'll give sort of a more mathematical definition of it. But like for people that know about it, it's basically, in this case, I'm thinking about four-dimensional gauge theories. Four-dimensional n equals 2 gauge theories are 4D n equals 2 pure gauge theory. With the gauge group being with the gauge group UR. Okay, so this is basically the only setting that I'm going to deal with. So R is always going to be fixed. There's going to be some integer that's at least 1. So my R's, people always complain that they look a bit weird. This is an R. There's no other letters, I think, that can be confused by us. Okay. All right, so what is the definition? So this is kind of for the moment, a quick definition. I'll sort of say a little bit more later. It's basically integral over the moduli space of instantons. So denote that as MRD. I'll give a definition later. So this is the moduli of instantons. And I integrate on this moduli space the fundamental class. Okay. Denote that 1 is the fundamental class. One thing to say for the moment is that this moduli space is not compact. So integration by integration, what I really mean is like equivariant integration. So the point is that there's a torus section on this moduli space, and the fixed locus is compact. It's just a collection of points. So this integration really means equivariant integration. And there are sort of, yeah.
Why don't you use in the lemma for compactification or something like that?
Well, you can't. I mean, the kind of base. This is it's like, so I'll talk about this later, but it's basically sheaves on P2, like frame sheaves on P2. So for instance, if you take R equals 1, this is like the Hilbert scheme of points on C2. So you can't compactify it because C2 itself is not compact. So
okay. I'm sorry.
It's not the moduli space of curves.
Yeah, I was thinking that it was. I didn't see it.
Sorry. Yeah. Maybe it's.
Yeah. Don't worry. I see it.
Yeah. And so yeah, so you just can't compare that. Yeah, so as I said, there is a torus action. So this integration means really equivariant integration, and there are equivariant parameters that are usually denoted epsilon1, epsilon2. Exactly the same. In gauge theory, these are somehow sort of called the omega background parameters. If you're sort of familiar with this kind of language. Okay, and the point is that, well, actually, yeah, I mean, this is not a very scary object in the following sense, that because they actually know very well how to, they understand the geometry of this modular space pretty well, so you can get like very explicit formulas for these subversion functions using equivariant integration. Okay. But one thing that's not at all obvious from that perspective is that there is, if you expand that this like Nekrasov instant partition function, if you expand in these equivariant parameters, you get a sort of genus expansion. So-called genus expansion. And that's, by that I mean that there's an expansion of the following form. If I take log of this guy, okay, there's some expansion of the following form. And why is this called a genus expansion? It's called a genus expansion because there is some perspective. There's a perspective in which you can think of these kind of free energies, G. So these are called free energies as, or at least there's an expectation that these should be sort of Gromov invariants of genus G. So that means that it's like counting some kind of curves of genus G mapping to some target. Okay, so that's where this name genus expansion comes from. Okay, and in this talk, what I want to, or like one of the questions here is like, well, what do these FGs really mean? So yeah, as I said, there's this expectation in that they should be corresponding to Gromov and free energies, but it's sort of a bit more complicated than I'm saying. And there's kind of maybe a different answer to this question as well, to what these FGs are, or what these should be. And that comes from Seiberg theory. And well, what's the statement? So this is a theorem due to Nekrasov and Nakajima-Yoshioka. And what it says is that this kind of leading term, so F0 here, so the genus 0 part of this thing, is an object called that can be computed purely from the geometry of a certain curve called the Seiberg curve. Okay. So the precise statement is that F0 is the so-called Seiberg preferential. Okay. Yeah, I don't want to really define what the prepotential is and get into details about this. But the only thing that I want to stress here is that it's something that's it's an object that's encoded purely in the geometry of a certain curve, of an algebraic curve called Seiberg. Okay. So all I want to say is that F0 is encoded in the Seiberg curve. Okay. And I'll tell you a little bit later, sort of one way to see where the Seiberg curve comes from this perspective, because it's not at all obvious that there should be something like this. But then this raises the natural question: well, what about the higher genus contributions, these FGs? Do they also have something to do with the Seiberg curve? Well, the answer is conjecturally yes. So I'll use this a little bit, this part. The question is, well, do the FG also, for G greater than 0, also have something to do with the Seiberg? As I said, there's an expectation that this is indeed the case, but this is not proved yet. So this is a sort of conjecture due to Huang from 2006. These guys, these FG. Are so-called free energies computed by a certain formalism called the topological recursion, which appears in my title, by the people sometimes call the Eynard and Orantin topological recursion. Also on the same curve, on the Seiberg curve. Okay, so somehow like all of this information is somehow captured by purely by this by the geometry of this curve. Okay. All right. So what's the point of my talk? Actually, I should make a. So whenever I talk about topological recursion, it's going to be in this kind of specific limit where epsilon goes epsilon to 0. If I forget to mention it, that's kind of always assumed. It's a very special point in the gauge theory, but there are some very nice simplifications that happen at this point.
Excuse me, could you remind us what was the epsilon 1, epsilon 2?
Yeah, so these were the equivariant parameters that I have from the torus section here. So
okay.
These are the equivariant parameters. Yeah. Okay, so what is the goal of my talk? Unfortunately, we can't quite prove this conjecture, so we don't know how to prove this. So now it's open for a while. But what we can prove is something analogous, not quite for the Nekrasov instanton partition function, which I just actually erased. But for the object that you have before this integration. Okay, so let me write it down. So the goal is to prove. So the goal for today is to prove an analogous statement for the so-called Gaiotto State. Okay, and the Gaiotto State denoted by G. So this guy is basically, if you remember the Nekrasov instant partition function, you can sort of still see it. It was an integral over this moduli space of the fundamental class. And the Gaiotto state is like basically if you just take the generating series, that's just the fundamental class. You don't integrate over the space. Okay, so let me write down definition. So So it's the cohomology class itself. It's summed over this like D, which is the instanton number. So I'll say what that is. But basically, you can just think of this the Gaiotto state as being like the fundamental class of the instanton moduli space. Okay. Right. So let me write down here, and then the rest of the talk I'll sort of give some sort of try and explain everything that I already introduced. So the theorem is that the Gaiotto state G also admits a genus expansion of this form. Genus expansion. Okay, and the expansion coefficients are computed by the same Eynard and Orantin topological recursion, which I'll always just abbreviate by TR. Say writing TR. Not on the Seiberg curve, but on a sort of degenerate version of the Seiberg curve, which we'll call the half Seiberg. And I'll explain also where this kind of terminology comes from, but it's some degenerate version of the Seiberg curve. Maybe one thing to say already at this point, and like the reason why it's in some sense this is like sort of easier than proving conjecture there, is that this curve is of genus 0, while that curve is like always of higher genus. So in the SU2 case, for instance, that would be a genus 1 curve. This is always a genus 0. Okay, is it clear what I want to prove? Yes. Yeah, please feel free to interrupt me and ask anything at any point. Sorry, and there's always this thing, whenever I talk about TR, I will probably forget to say this, but it's always at epsilon 1 plus equals 0. Okay. Okay, so let me start by saying a little bit more about the instanton moduli space and the Gaiotto space. So the moduli space, instanton moduli space, that I denote as MRD. So R, remember, is just some integer that's at least 1, and D something that's at least 0. Okay, so this is the moduli space of rank R torsion-free sheaves. P2 framed. Okay. What does this framing mean? It just means that it's a. So let me give the sheaves a name. So if I restrict to the line of infinity, the framing is an isomorphism, is a trivialization of the sheaf. All right. So this has many. This is sort of simpler descriptions if you want, and depending on your perspective, it has a description as the GIT quotient. So using the ADHM construction. So it's a space that we can really get our hands on in some sense.
And with the framing, you have it compacted model space? Or?
No, the framing, the sort of partially compact framing model space comes from the fact that you're not taking vector bundles, but you're taking torsion bundles. But the framing still doesn't compactify the model. But yeah. I mean, so for R equals 1, somehow, you know, the modular space ends up being the Hilbert scheme of D points on C2, which is like, yeah. So it doesn't make it compact still because it's points can go away. Yeah. So the space is not compact. So it is smooth, but not compact. Yeah, and as I said, for R equals 1, this guy is the Hilbert scheme. And that's a pretty good example to keep in mind. A lot of the geometry of the space essentially boils down to the Hilbert scheme points. Let me see something else. Yeah, it's a yeah. I mean, okay. One important thing that we need is that because it's not compact, we will want to work with sort of equivariant cohomology, so usual cohomology, and for that, basically there's a torus action on the space. Okay, so there's a torus, which is it's an R plus 2-dimensional torus. And I'm writing it separately because the R and the 2 sort of play different roles in this action. So what the 2 does, the C star squared, the 2-dimensional torus, acts on the base P2 itself. And the R-dimensional torus basically acts by changing the frame. So this guy acts on the base P2. This guy acts on the frame. Fact is that the torus fixed locus is compact, so it's just a collection of points. And we can even say more. There's sort of, if you think about the Hilbert scheme example, they're basically indexed by partitions. And if you think about the sort of general R case, what that means is that it's not partitions, but it's like R collections of partitions that sort of add up to this. So we also have a good handle on what the fixed locus is. So fixed locus is compact. So we'll work with the equivariant conjecture. Something like this. This is the torus equivariant cohomology. And here we can consider the fundamental class of this modular space that I'll denote 1D. This guy is the fundamental class. And I can finally give a definition of the Gaiotto State. This guy's going to be living. And this guy. Okay. All right, so this is basically the object that we're interested in. Okay. Yeah, just to remind you, how was the Nekrasov instanton partition function defined? It was defined as basically taking that Gaiotto state and integrating it, okay, over the moduli space. So it's defined by integral for some. Maybe it's worth writing it like this. So, in sort of, yeah, in physics literature, for instance, you'll see it written in this way. And it basically, and I'll sort of explain the reason for this a bit later, but I mean, for the purposes of now, you can just take this to be the definition of this integral, okay, of just the integral of the Gaiotto state, except that I put, instead of lambda to the RD, I put 2 times R times. Oh, maybe this is something I didn't really mention, but like in physics, like this lambda usually appears as kind of the energy scale of the theory. So it's like some cutoff for the partition function for the integral. Okay. Good. Yeah, so I have like half an hour.
Yes.
Okay, so all right, great. So this was kind of all about the kind of gauge theory side of the story about the Gaiotto state. Now let me say a little bit about, well, how do you see this curve side of the curve appearing, and like, you know, what does this curve have anything to do with this four-dimensional gauge theory? So that's the question that I'll try and answer now. So how does the Seiberg curve enter the story? Maybe sort of, yeah, there are maybe a few different answers one can give to this question, but like the perspective that I want to take is this perspective of the AGT correspondence. So let me explain that. Perspective. So the AGT correspondence is basically, it's saying that there's sort of a duality between four-dimensional gauge theories on one side and two-dimensional conformal field theories on the other side. Okay, and so everything that I've been saying so far is about the kind of four-dimensional side, and the Seiberg curve appears on this kind of two-dimensional conformal field theory side. So this is due to Alday-Gaiotto-Tachikawa, 2010. And their motivation for this was like considering some kind of, or where their intuition comes from is the following. So you take some kind of six-dimensional field theory, and then you can compactify it either on sort of this two-dimensional surface to get a four-dimensional gauge theory, or you can compactify it alternatively on the four-dimensional side and get a two-dimensional conformal. And so they basically, what they claim is that these two theories, because they come from the same kind of six-dimensional theory, that they should be equal to each other. So that's kind of where their predictions come from. But out of this kind of idea of the six-dimensional theory, they come up with like some very concrete mathematical conjectures. Okay, so let me basically explain what that is. Okay. So basically, the first thing is what I just said in words. So there's sort of four-dimensional gauge theories on one side. This is actually much more general than the setting that I'm talking about today. The one that I'm talking about is like a very specific example of this correspondence. Our dual to 2D conformal theories. Okay, so and the gauge group on this side, which we take to be UR. Well, I'm not going to say much about conformal field theories, but like so the mathematical way to think about conformal field theories is that they have something to do with representations of a vertex algebra. Okay, and so the group on this side goes to that corresponding algebra on this side, and the algebra is this so-called W-algebra of the Lie algebra that's associated to this group. So it's GLR in this case. Okay. So everything that's happening on this side is something to do with representations of the W-algebra of GLR, which is a vertex algebra. And so all the objects that will appear on this two-dimensional side will have something to do with this algebra. Okay, and more specifically, what do they say? The object that we've been considering on the 4D side, remember, is this Nekrasov instant partition function. What does that correspond to on the 2D side under this duality? So Nekrasov instant partition function. That corresponds to, on the 2D side, what's called a 2-point conformal. 2-point irregular. These are the sort of things. I mean, they're sort of like, you can think of them as like the building blocks of correlation functions in your 2D state. Okay. But actually, from this, you can extract a sort of a very clear mathematical statement, which is that, remember that this Nekrasov partition function was built out of the Gaiotto state. So you can ask, okay, what happens to the Gaiotto state? And that should go to a certain vector in a representation of this W-algebra. Okay? And it's a specific type of vector called a Whittaker vector. In a specific representation of this algebra. Okay. All right. So now this is like a purely mathematical statement. Actually, I mean, I didn't write down all the details, but like basically from this you can deduce what this representation should be and what conditions this vector should satisfy, and these conditions actually will determine. And this is a theorem of Maulik-Okounkov and Schiffmann-Vasserot. Independently using different techniques in 12. And it says the following. So this kind of states where the Gaiotto state lives. First of all, they identified with the representation of the W-algebra. Okay, so first part is that this guy is a Burma module. Oh, maybe before I say that, let me sort of say a little bit of yeah. So these algebras are sort of, I mean, these vertex algebras, if you don't know what they are already, they're sort of like, you can think of them as like some kind of infinite dimensional Lie algebras. But that's not technically true, because if you try to write down kind of the commutation relations between the generators of your Lie algebra, quote unquote, you will get some things that are nonlinear. So it doesn't really look like a linear algebra, a Lie algebra. So it's some kind of nonlinear Lie algebra is one way to think about vertex algebras. So an example, and I'll talk about this in a second, is that if you take R equals 2 and you take SL2 instead of GL2, then the algebra that you get is this Vasserot algebra, which is well known. So that actually really is an infinite dimensional Lie algebra. Okay, sorry. So let me go back. So because I'm saying Verma module, so that's kind of the spirit in which you should interpret the statement. It's a Verma module of this algebra. Okay, so basically the space where the Gaiotto State lives is a Verma module for this algebra, for this vertex algebra. And the Gaiotto State, which lives in there, is a Whittaker vector. This one. And in fact, so this is, it's a bit more specific than I'm writing it down here. What I really want to say is that, in fact, it's a specific vector in this module, and these conditions of being a Whittaker vector determines it uniquely. Determined uniquely. Okay. Yeah.
If instead you were mentioning the case where you use SL
Yeah.
instead of GL,
Yeah.
and then don't bet the duality, to which would that?
It would be SUR here. This would be the SUR.
Okay.
Case group
Yeah,
would be SUR.
of course.
Yeah.
You can you do it with any other subgroup of GL?
So yeah, you can do it for, I mean, yeah, so that's a great question. So basically in the way that I've said it, yeah, there are various difficulties. Okay. So the statement, the physics statement holds for any groups of type ADE in exactly this form.
What?
ADE.
ADE. Okay.
In the sense that, you know, the Nekrasov instant partition function will correspond to the irregular conformal blocks. The problem is that if you try to look at the instant moduli space, it's singular already in these ADE cases. So you have to do something kind of a bit fancier. So you have to work with some kind of intersection cohomology to make these statements. And then the statement for so this kind of statement is expected to hold, but it's not proved. So this is something that's not proved. Somehow we don't have the tools that are used to. Sorry, no, this statement is proved in the ADE case. This is a result of Braverman, Finkelberg, and Nafima. But what you have to do is like not work with equivariant, like you have to work with sort of intersection cohomology because the spaces are singular. So it's more complicated. Okay, if you go beyond ADE.
But still, you will have a correspondence to a 4D.
Yeah. So you start with the 4D gauge theory of group type ADE.
Okay. And then you get to.
And then you will get the corresponding W-algebra. You will get a Whittaker vector for that W-algebra, which is going to be the Gaiotto state in your gauge theory. So for ADE, actually, sorry, everything that I said is basically true if you just replace, if you kind of replace the groups everywhere and the corresponding W-algebras. And if you replace the equivariant cohomology, the kind of usual equivariant cohomology by intersection cohomology, equivariant intersection cohomology, because the spaces are singular.
Okay.
Beyond ADE, it's more complicated. Not exactly the statement is not even expected to hold. You have to do something a bit more complicated, which has to do. I mean, maybe this is something we can talk about a bit later. But basically, you have to look at some kind of you have to try to get the other groups from the ADE groups by like doing some Lincoln diagram foldings, and then the kind of folding symmetries for the Lincoln diagrams appear as some kind of. So you have to look at states. You have to look at representations that have this kind of extra symmetry on the symmetries. So it's a bit more complicated for the other cases. But yeah, let's do this.
Thank
you. Cool. Okay, so I'm not writing down very specifically what a Whittaker vector is here, but let me actually write it down more explicitly for the SUG case. Right. So example. Let's see. So I mean, you don't really have to worry about the fact that I'm going from U2 to SU2. They're sort of basically the same because you can sort of, yeah. I mean, the W-algebra of GL2 doesn't change that much for SL2. There's just kind of the trace bit of the matrix that you can sort of factor. So basically, it's sort of, you can think of it as the same. It's the same thing. Yeah. So then the algebra on the 2D side is the W-algebra SL2, which is the Vasserot. This, you quickly recall, an infinite dimensional Lie algebra with generators that each denoted Li. I is anything in Z, and a central element C that commutes with all of these generators. And these guys have the following generation ratio. Li all J, epsilon minus J, J plus C12. Delta I plus okay, so some infinite dimensional algebra. It's like there's everywhere in physics, especially in conformal theory. Vasserot algebra is like kind of a subalgebra of all of these algebras. So there's always things in there. But in this case, it's the full W algebra. And the Whittaker conditions are the following. It says that if I act by Li on my Gaiotto state, this is 0 for all I that's at least 2. And for L1, acts diagonally by lambda squared. So this is how L1 acts, Li acts. And you should see this as like kind of a slight generalization of what a highest weight, what the highest weight state. The highest weight state would just be killed by all the positive modes of the Vasserot algebra, so everything that's at least 1. But a Whittaker vector is somehow like a slightly different version where L1 acts by lambda squared and then everything else acts by 0. So if I set lambda to 0, then I really get the highest weight state, and this is something more complicated. Okay. And the conditions for the general W algebra don't look very different. Just didn't write them down. Okay, so finally, let me tell you. So this was the question: how does a Seiberg-Witten curve appear in the story? And that's kind of what I wanted to explain all this. This is maybe a slight cartoon picture, but again, it's using this AGT story. Basically, we're looking at these kind of 2-point conformal blocks. So you should think of that as like kind of conformal block where you sort of insert 2 irregular singularities, so somehow like 0 and infinity if you want. And where you're putting these singularities, you can think of, in some sense, as inserting these guys. So the G here, the G here. Okay, how do I get the curve? The prescription is as follows. In the SU2 case. So I'm still doing the SU2 case. You take the curve to be y squared equals. You put one Gaiotto state on one side, okay, with the other one on the other side, and then in the sandwich you put the Vasserot field. So that means I put Li over x to the I plus 2. I sum over all I. Okay, so it's just a generating function of the Vasserot algebra generators. It's called the Vasserot field. Okay, and then it's not too hard to see now. So this is the prescription. Okay, this is the sort of AGT prescription, and I think the limit is epsilon 1 and epsilon 2. Okay, so now we just need to think about what that does. So I told you that Li acts on the Gaiotto state by 0 as soon as I is at least 2. Okay, and 1 acts by lambda squared. So I get lambda squared over x cubed. I don't go anything higher in higher poles of x. Okay, L0 acts by something. Let's call that something u. And then how L minus 1 acts on the left side is the same way in which L1 acts on the right side, okay? Which is again this lambda squared. And similarly, L minus 2 acts on the left the same way that L2 acts on the right, so you get 0. So you're going to get 1 on this side. Okay, and this gives you some on this side. This guy's a hard. Okay, so this is somehow how you see the curve appearing that's controlling the gauge theory on the 2D side, right? Which is like going exactly through this kind of description that for what the Nekrasov partition function. Okay, so yeah, I mean in this case it's actually genus 1 curve. So it's starting to run out of time now. Okay, so we understand hopefully the Gaiotto state and how you get the Seiberg curve kind of coming from the CGT perspective. And the last thing I want to tell you about is about topological recursion, which was the thing that I said, well, actually you can compute all the kind of genus expansion coefficients of the Gaiotto state from a curve. It's not going to be the Seiberg curve, it's going to be a different curve. I'll show you how that curve appears as well. Okay, so that's kind of the last part of my talk. Should be hopefully done more or less sometime. So yeah, topological recursion. So some historical sort of context for this topological recursion is that this was introduced by Eynard and Orantin when they were studying the large and expansion of matrix models. So matrix models are sort of like made into, like, you can think of them as like zero-dimensional QFTs in some sense, where you're integrating over the space of matrices. So it's like you integrate over the space of Hermitian matrices, for instance, with some potential. And you look at what happens when you send the size of these matrices to infinity, so large matrix expansions. And what you see is that the kind of partition functions that you study in this setting also have a genus expansion. And what they realized, I mean, this people knew already, but what they realized is that the higher genus kind of contributions that appear when you do this large n expansion can be computed by just knowing something about the kind of genus 0 part of the story. And this genus 0 part is stored in precisely the data of a curve plus a little bit more data, which is usually called a spectrum. Okay, so what they did is actually, well, they realized that this formula is somehow quite universal. It doesn't appear only in the study of large n matrix models, but also in the study of various other enumerator problems. For example, Hurwitz theory, or like computing volumes of various moduli spaces, like volumes of hyperbolic moduli spaces that Mirzakhani computed, or kind of psi-class intersection numbers that is in the style of Whittaker and Seiberg, and sort of various many other problems as well. So it's kind of a very, very sort of general, powerful technique. And what we realize here is that it appears in this context as well. So this is due to Eynard and Orantin. And the idea is as follows. I won't write down the formula for you, but I'll tell you what the formula does, or what the intuition, some intuition for what the formula does. So basically, think of like topological recursion as some blind box. You feed into it the initial data, which is called the spectral curve. So this is the data of an algebraic curve. So let's see some Riemann surface. A meromorphic function x on this Riemann surface. A differential of omega 0, 1. And another object omega 02. So omega 01 is a differential on C, meromorphic differential on C. And this guy is a bidifferential on C. Okay. I don't want to get too much into what that is, but basically you can think of it as a data of a curve with a little bit more depth, which is this spectral curve. And okay, what it produces for me are some differentials, omega gn in general. Okay, so g is going to be some integer that replaces 0, n as well, and these are n differentials on the same curve C. They're symmetric as well. Symmetric. Okay, so what's the point? So sorry, and so here I want 2g minus 2 plus n to be equal to these to the 0. So some of the idea is that you have this kind of low genus, what we usually call unstable kind of data, which is the 0, 1, 0, 2 data, and from that on the curve you can build all of the kind of higher genus data, so the general GNN data. And the stability condition is something that you'll realize, right, if you've seen the multi space curves. These are kind of stable curves. And so usually this appears in problems where you have where you're counting like, something to do with the multi space of curves, or like, doesn't have to be multi space of curves, but somewhere where there's like sort of some kind of genus expansion. Okay. Yeah, so why is it called topological recursion? This formula is recursive on the Euler characteristic, 2g minus 2%. Recursive definition. So something else. Yeah, and the formula is like, it's not so bad. It basically models like a pair of bands decomposition. So in some sense, it basically tells you that you can build omega gn by everything of lower topologies GNN if you just kind of remove a pair of bands in all possible ways from this genus G and marked by the surface. So that's kind of what the formula is. So models the pair of bands decomposition. Okay, I won't say I'm getting pretty close now. Okay. All right. So let me get to this statement. Can I? Yeah. Can I like 5 minutes?
Yes. Yes.
Okay. All right. So let me set epsilon 1 plus epsilon 2 equals 0 now always. Okay. So this is some special limit. I denote h bar to be minus epsilon 1 times epsilon 2. Okay, so basically now that's my only parameter. I'll need more space, so we'll go back here. So somehow the first kind of lemma, if you want, is that this Gaiotto state admits a genus expansion in the following form. I take log of this guy, and this is in h bar. Now you get a genus expansion. So G is at least 0 and it's at least 1 of some objects that's called FGN, where these FGNs are, you can write them more explicitly as depending on like tuples, AI, KI, so A1, K1, A2, K2. So these T's are some coordinates, like for the this is basically a basis for the instanton, the equivariant cohomology of the instant modular space. Right? So everything is happening there. Remember? So and then this over ai's being from 1 to r, and the ki's being at least 1. The t's tak is a basis for this instanton cohomology. And the theorem is that these guys, these expansion coefficients here, so this is our theorem with Gaiotto and Giacomo Umar, is that FGN let me say the data of FGN is encoded in omega GN. They're basically the same, essentially. You can think of the omega GNs and the FGNs are essentially the same data. Computed by topological recursion on now this half-sided curve. Okay. And what I want to do to finish is basically to tell you what is this curve, what is this half-sided curve, and how do you see this from the UNED perspective. So maybe one thing to note is that this curve is of genus A, which is why somehow everything is easier than doing the Nekrasov partition function. Okay, so let me just go back to this SU2 example. What you're actually doing is somehow looking at a half of the theory that we had in the previous. What do I mean by that? Well, actually, if you remember earlier, to get a Nekrasov instant partition function, you had two irregular singularities, and you were sort of thinking of inserting like a Gaiotto state in each of these guys. In this case, what we have is we just have one irregular singularity, if you want, where you insert the Gaiotto state, and the other sort of puncture, if you want, you don't insert anything. And inserting nothing basically means inserting the highest weight state. So let's say the highest weight in this case is A. So insert that on the left, and insert the Gaiotto state on the right, and then I do the same thing as before, which is to insert the Vasserot field in the middle, so I get this image. All right, so now it's kind of similar calculation as before. Right? So we get Li(x) by 0 as soon as I is at least 2. So L1x by lambda squared. So I get lambda squared over x cubed. Okay. L0, well, instead of thinking of what it does on the right, which I don't know, I can think of what it does on the left, and the x way is just the highest weight. So A over x squared. And now, for the same reason as before, all the the negative modes, so the L minus i's, they act on the right by Li's, but they all act on the highest weight state, and so all the positive ones act on the highest weight state by 0. So that's a curve in this case. And you can think of this curve, so this is the reason for calling this the half-sided curve. And this appeared, like this kind of terminology already appeared in this picture already, well, sort of this picture appeared already in a different perspective in some work of Lotte Hollins and Digraph, where they're sort of looking at some kind of string theory constructions, but essentially this name already appeared, so we use the same thing. Cool, and this is unit 0 curve, so everything is great. can actually compute things much easier. And basically, I won't get into the proof of this statement, so this is kind of what we prove, and it's always a genus zero curve for any R, even though I just showed you what happens for R equals 2. Okay, that's a good place to stop, I guess. Thanks very much.
Thank you. Kuntal has a question here on the internet, on the channel. Says if the stability that you were using in the multi-speed of shifts, it was Giesecke stability.
Yeah. So I mean, well, essentially the stability is, yeah, it's kind of like, yeah, slope stability if you want for the frame machines. So it's, yeah, basically yes. But the point is that.
But when you have framing, sometimes you use the framing. You have an extra parameter with the framing or something. Nothing. I mean, moduli speed of frame shifts was constructed by Hurwitz, no? Hurwitz and somebody else. Essentially.
Yeah. So
usually. I mean, the frame appears in the stability or not?
So in this case, somehow, basically, all the torsion-free sheaves are already stable, just because, yeah, essentially, the point is that the framing, like when you look at the kind of framed stability, you look at what the subsheaves should do at infinity, right? At this kind of line infinity, which you find. And the point is that, like, basically for these torsion-free sheaves that you're looking at, they already automatically satisfy the framing at infinity, just because they have to be kind of twisted by something lower, so in order to get the frame. So okay. So in this case, I mean, yeah, I mean, if you want, we are looking at sort of there are no strictly semi-stable sheaves. There are only stable sheaves, and these are kind of all of them. I mean, yeah. Okay. The stability also you can see from the GAT perspective. So there's basically sort of like two choices of stability that gives you the smooth ones, and they just kind of flip from like choosing or one as your ample bundle if you want to.
Well, I hope this answered this question. Does anyone have any other question?
Yeah, I have an even more technical question about that moduli space, because with moduli spaces of torsion-free shifts, I'm used that at least a general element is locally free, but in this case it's not locally free unless unless G equal to 0. So what is a general element? How can I say a general element in that moduli space? I mean, I can imagine a locally free sheaf of degree 0 tensor with the ideal sheaf of G points, but probably this is not the general element, right?
Yeah, it's not. So yeah, this I don't know. I have to think about this. What a general element looks like. Yeah, sorry. Let me think about that and answer you a bit later.
Okay, another question, maybe simpler for you. I'm puzzled with the formula there of the FGN, because you have FGN there, and then it seems that the A's, K's, and these T's are cutting your FG. Am I right? Because
yeah. So I'm just expanding these guys in like some bases for the cohomology.
But this is cutting the because so the sum of all this makes one.
Sorry,
you have FGN and then inside the sum you have FGN again.
Yeah, sorry, maybe this is bad notation. Maybe this is bad notation. So maybe I should call it, I don't know, FGN. So basically what I want to say is just that
I see.
I take the FGNs and I expand it in some bases.
There. Okay,
and these are just some coefficients. Yeah, sorry. That's bad notation.
Very easy question. Apart from the difficult ones. Any other question there? Yeah. Okay, then thanks the speaker again for this travel over these many theories. Thank you.